All right. Yeah, thank you for the introduction. So today I'm going to be presenting about some research and development experiments that I conducted with my colleague in pursuit of some very specific problems on a blockchain called the Secret Network. For those of you not familiar, Secret Network is a blockchain that runs on the Cosmos SDK stack, and it offers a decentralized confidential computing platform. The way that it works is it compiles smart contracts using COSM-WASM. So you can write your smart contract in Rust, for instance, compile it to WebAssembly. The validator set runs trusted execution environments. The WebAssembly code gets loaded into the enclave, and the trusted execution environment has attested to the chain. The validators actually signed the inputs from users when they execute the smart contracts. So all of the inputs going into the enclave have to be signed by the validator set before they are executed. So a malicious node can't just execute arbitrary smart contract commands. And the outputs are encrypted so that only the user who executed those inputs can decrypt the outputs. So on Secret Network, there is a standard interface for smart contracts that defines tokens, the SNP-20. And the naive implementation of the smart contract stack that enables these sort of token transfers turned out to have a privacy vulnerability regarding storage access patterns. So if you're familiar with what oblivious RAM is good for, this would have been a case where it would have prevented this type of privacy vulnerability. This is the first thing I'll be talking about. We implemented a novel solution entirely within the smart contract itself without requiring any changes to the light client that runs in the enclave or to the core network code. We did so by using some interesting data structures that I'll talk about. The part 2 of this talk is about a sort of unique problem to running trusted execution environments where you are providing a decentralized confidential computing platform, which is that whenever you have clients that need to retrieve data from the private database that the contract is holding on behalf of their data, there are certain, this is very computationally expensive when you have, many users just trying to request some simple piece of data. And it turns out that we can actually reduce the load on these nodes by moving those operations outside of the enclave. And it turns out that there is a way to do that leveraging fully homomorphic encryption. And then finally, just some status on where this work has led us. So storage access patterns. What really is happening is you have, let's say you have a transfer from Alice to Carol. So Alice wants to send Carol some tokens. You have a private database over here that represents the balances of each of these users. And when this transfer event occurs, this database, although it is encrypted, it actually lives in storage outside of the enclave. And the reads and writes to this storage area is a side channel. So an attacker can see which specific rows in this key value database are being read from and written to, and they can actually monitor the timing of when those reads and writes are occurring. And this is the basis of storage access pattern vulnerabilities. So this is mainly a problem for tokens because all you have to do is monitor, what is the first row that's being accessed? That is your sender. And then what is the last row being written to? That is your receiver. So naturally, if you want to de-anonymize who the recipient of some third-party transaction is, you can start to just brute force, take guesses at who you think that recipient might be, and monitor your own writes. And once you find a match to that row, you have now de-anonymized that transaction, and you can deduce that the recipient of that third-party transaction was Carol in this case. So as I said before, oblivious RAM actually is perfect for this, but it is computationally expensive, and it is sort of an all or nothing approach for this very niche thing, because for a secret token, you only have this balances database that you want to protect. There is lots of other types of storage that you don't necessarily need oblivious RAM for, and thus you would be paying quite a large penalty, and it is something that you would have to implement at the core network layer. So it's quite complicated. I'm not saying that it's not ideal. Perhaps with more research, there could be a solution that involves oblivious RAM. But today I'm going to be telling you about an approach that is cheap and efficient and works quite well. Finally, some other platforms will use, for instance, I'm forgetting the name of the token, but ring signatures. Basically, you create decoys so you can send to a group of recipients, and it is not clear which recipient was the actual recipient, and you're creating a closed anonymity set. This works well if you have a consensus mechanism built into this ring signature process. But another approach called, simply for lack of a better term, decoys, where you require the client to provide a set of recipients that act as decoys. This is a challenge because now you're requiring the user to pick the perfect anonymity set, and the user does not have the knowledge of how to construct the perfect anonymity set. So yeah, as I said before, let's see, what is this? This will always identify who the recipient is, and an attacker can unmask. All right, so yeah, a different representation, different diagram of the same problem I talked about before. So you have your secure enclave, and then you have your encrypted key value database. So you have the recipients, each key is encrypted, and the balances are encrypted, but each row corresponds one-to-one, and this is what an attacker sees. It's all encrypted. Okay, so when the contract needs to access a balance, it starts with the address of the recipient. It knows how to encrypt that because it has a shared secret with the trusted execution environment. It accesses that row for Carol's key. It gets the encrypted value back, and an attacker is able to see this read, gets the balance, and then decrypts it. Okay. And again, this is what the attacker sees of the database. It's all encrypted values, but they can see the exact row being accessed. So the basic concept of smoothing is that, or one way to achieve smoothing is just bundle everything into a single row, essentially. So you create a group of recipients or a group of accounts, and now anytime you need to access one of them, you're accessing the same exact row in that database, and the attacker is none the wiser as to whether you accessed Carol, Bob, Alice, Zach, etc. This is the basic concept. So what we did is we introduced this data structure we called the delayed write buffer, and it's a fixed width vector that gets read from and written to back to storage on every execution under the same key. What it does is that it actually will delay by a random number of executions when that entry gets moved to the storage area. So what this looks like in practice is, let's say that Alice sends 50 tokens to Carol. First thing that it does is that it loads this fixed width vector from that from that static key. Let's say there's 16, there's a capacity of 16 entries. So that read is always seen at the top of every execution. So an attacker learns nothing there. Then we have to check and update the sender's balance. So we read Alice's balance, and then we remove 50 tokens from hers. So at this point, an attacker can still see who the sender is. We haven't granted any privacy to the sender. The next step is that we update this buffer that we have now in memory. So we're going to add an entry to increase Carol's balance by 50. But to do that, we have to evict an entry from the buffer. And this is the part where we achieve privacy, because we will randomly select one of these entries to evict. And the randomness is provided by secret VRF, which is verifiable randomness, provided by the validator set. So we randomly select Bob to evict from this buffer. And then the next step is that we write to Bob's balance, okay? So an attacker can see that some row was written to. However, they have no idea which transaction in the past corresponds to Bob receiving those tokens, because it could have happened 1 transaction ago, it could have happened 10,000 transactions ago. And this is what that, this is a curve, this is a set of curves that represents what that probability looks like. So it is a probabilistic privacy model. And for a buffer width of k, the probability that an entry hasn't been accessed after n executions is modeled by this equation up here. Another way to think about this is if you set that buffer width to 64, then the probability that a given recipient has been flushed to the storage area where you would be able to see that movement to that storage area, the probability of that, when that certainty reaches 99.5%, this is roughly equivalent to an anonymity set size of 350. So that's one way of reading this chart. So let's see, the k equals 64, this blue line right here. After, yeah, it goes off into 350, it's off the chart. Okay, so what do you mean by machine crashing? It is in the smart contract's ephemeral memory during an execution, which is running inside of the trusted execution environment. And that memory of that buffer gets written back to storage before the execution ends. So it's written back to the database. So it's one execution on the blockchain, if that makes sense. Okay. Okay, so there is two certain types of attacks that you can perform on a data structure like this. One is that you can just send to the same recipient over and over and over again. And if you're always evicting a random entry, you're going to fill that buffer with the same recipient. Now you basically know the exact storage key that's going to be written to. You write a different address, and then you just wait for that key to flush. So to overcome this, we simply accumulate to the same recipient. So if we send more to Carol, we just update her entry in the buffer. We don't randomly select. We specifically choose. However, there is still this other problem. Well, what if you just flood with a set of known addresses? Let's say you have you control 1,000 addresses, and you just send different ones, and you monopolize the buffer, and then you record the storage keys that are written to. Then you wait for a foreign party to send to someone, and then you flood again. You just monitor until you see the key that's not belongs to your set. And this is where part 2 comes in. 5 minutes. Oh, wow. Okay. So part 2 is about creating a complementary data structure that applies the same basis that I talked about before about smoothing, but to the storage area itself. Quick overview of this, and then I'm going to have to hustle through the last part of the slide deck, is we have this data structure that is a bitwise trie, and we want to insert a new entry for Edgar, who received 10 tokens. And the trie contains bucketed tables. So we have our same database again, but this table has a capacity of 4, so it is now full. So what we do is we split that node, and this is based on a prefix of the hash of the recipient's address, concatenated with a secret that the contract has, so that an outside observer can't predict how this trie will form. We need to insert Edgar in the left node again, so we split one more time, and finally Edgar fits in this. So this is how this data structure grows. Okay, so the last part. As I talked about before, with secret tokens, all you're trying to do is request a very simple value. So this confidential computing is a little overkill because you just want, what is my balance in the database? And it's doing a lot of work just to decrypt your inputs and encrypt it and send it back. The idea is, let's move that workload outside of the enclave, and we can do this with fully homomorphic encryption. I'm going to skip this part. The basis of how this works is that normally you have a bunch of users putting a workload on this trusted execution environment node, but if we can move some of that workload to non-trusted execution environment hardware, we can scale much more easily by moving parts of the workload to cheaper hardware, because it is more expensive and less available in the cloud to provision trusted execution environments. And this is where heaps comes in. So fully homomorphically encrypted and authenticated private storage. It is simply put an L2 storage mechanism or a cache for these private databases that lives outside the enclave. And it is unidirectional, so it is essentially a way for the contract to push instructions outside the enclave. It is also authenticated, so contributors who run these nodes cannot deceive clients, and it is also oblivious, so it is free from storage access patterns. The way it works is, let's say that Alice sends some tokens to Bob. So the first thing that she does is she executes the contract with the amount and the recipient. The contract encrypts some instructions, which it then emits into the logs of the transaction. So this is public, but it is encrypted. The heaps node, so this is, again, hardware that is not running not on trusted execution environments. It is supplementary. It is basically a L2, has its own database for this contract of these fully homomorphically encrypted payloads, that it evaluates this instruction on. It updates each row, and then the intended recipient is the only one who can decrypt the row associated with their public key, and this is how they're able to get their balance up to date without having to execute anything on the trusted execution environment. So that's what we mean by unidirectional. It's one way. And the fully homomorphically encryption component simply guarantees that we don't have any storage access patterns that would leak to the heaps nodes that are monitoring these instructions. The benefit, however, is that the storage retrieval is incredibly quick, because the user, when they query these heaps nodes, all they have to do is retrieve a row in a key value database, followed by decryption. And this is a demonstration of that. So you have this database where the key is some public key, and the contents are actually encrypted with authenticated encryption. So only so there is authenticated encryption with additional data, so that there is proof that this information was actually indeed signed by the contract, which is its storage, or excuse me, the user's balance in the token case. And then that content is fully homomorphically encrypted with some adjacent bits about who the intended recipient for this information is. And so the recipient of the data, well, let me put it this way. The reason for the fully homomorphically encrypted component is because we need to update a single one of these rows. So we need to change a single plain text, but mutate all ciphertexts. This is the reason for the fully morphically encrypted component. Still good? We are done. Okay, so we are done. Thank you. Maybe time for questions, though? Okay. Any questions? I can maybe squeeze in a bit more info about this question.
In the interest of time, maybe we can have one question and then we can take it to the break for questions. So anyone?
Okay. Thank you very much.
Please give it up for Blake.